Hello, everybody, and welcome back to Pre-Calculus with Mr. Beck as we continue our journey through mathematics. Remember, if you have any math questions, I've got your back and you've got your back. So today our discussion is revolving around polar graphing. If you remember last time, what we talked about was we first graphed some points in what we called the polar coordinate system. So we took x equals r cosine theta. We took y equals r sine theta. So x equals r cosine theta. We took y equals r sine theta. And we also had tangent of theta is y over x. And we had x squared plus y squared equals r squared. Those are the four equations that we use to convert between the two coordinate systems. Today we're going to try to graph exclusively in the polar system just so that we could see what these graphs look like. And some of them, it ends up showing some simplicity. For some other of these graphs that we're going to be looking at, it's going to show some kind of deeper connections. Some of the connections that I think we're going to make are going to involve some astronomy, could be some physics in terms of if you have revolutions. And really the benefit of using polar graphing is anything revolving revolutions. So let's go ahead and get started. First objective we're going to look at is we're going to take a look at some of these polar equations and see if we can identify what graph comes out of these polar equations. So let's start off with the first one, r equals 6. Now, what this means is we have a graph that's generated purely from a radius. And this is where I'm going to jump back into my geometry knowledge to say, oh, in geometry, a circle is created. So a circle is created by just having a radius and taking that radius and revolving it around. So this should be a circle. And if you remember, the circle is going to be generated from the pole. The pole is what we used to call the origin, but in the polar graphing system, we call it the pole. And we're going to start by going out a radius of 6. And so if we go out a radius of 6, we go out 6 this way, we go out 6 this way, we go out 6 this way, and we go out 6 this way. Now, if you notice the type of graph that I have on here, it's sort of a mixture between the polar graph and the rectangular graph. And what I like about having that is it allows me to see what is this graph going to look like in a rectangular system. Maybe if I'm going to be graphing some points, sometimes it's more beneficial to graph it in a rectangular system. But with all these different things in mind, I might try to put both graphs together just so we can try to get a representation of each one in each system. So as we look at r equals 6, once again, we said that this is a circle with a radius of 6. The nice thing about the polar graph on here is this radius of 6 is something that I can very easily follow. And continue on. And if your circle does not look perfect, that is okay. If you remember, perfect circles and what I talked about in the classroom about perfect circles, not very many people can actually draw them. So remember, how did we get that coordinate, or how do we get that circle? We know in geometry that the radius being 6 gives us just the shape. But if you remember, what we did was we said, let's square both sides. So r squared is 36, and then we can convert r squared into x squared plus y squared is 36. Now, do we really need to do all that work converting from one to the other? No, we do not, but sometimes it's very beneficial to say, how do we get there? And I, especially in the first series of videos that we're doing today, we're going to be talking about how, how these do match up. We're going to try to go exclusively polar if we can. But you know what? It's always good to go back and say, where did this come from? Because we're re-emphasizing a lot of those skills back from 9.1. So I don't know if you remember what this one looks like. Theta equals 5 pi over 3. This is a graph that's based purely off of the angle, where the other graph is based purely off of the radius, which is why it created a circle. This graph is based only off of the angle. So if we look at where 5 pi over 3 is located, if you remember, that should be our quadrant 3. This angle gives us a 5 pi over 3. So what this means is we can have any radius generated off of that angle of 5 pi over 3. Now, if you remember also from last time we talked about, we don't necessarily just have to have positive radii, we could also have negative radii. If we have negative radii, we could be going backwards in this direction. And last tie to what we did in 9.1, this does not have to be written just as theta equals 5 pi over 3. This is also the graph of theta is negative pi over 3. If we look at that from if we go backwards along our quadrants. Or we could also say, so this is an or we could say theta is 2 pi over 3. Now, what is it that I want you to know from today's notes and where we're going? I want you to know that if you have an equation that's based purely off of the radius, we get a circle, and the circle is, and let's actually talk about this, this is centered at the origin, so centered at the origin. So if we have just a radius, we have a circle centered at the origin. If we have just an angle, we have a line that goes through the origin, or the pole, because that's where we're going to be referring to it now. And if you do remember how we created that, was we took the tangent of theta, or really a tangent of both sides. So tangent of theta is tangent of 5 pi over 3. Tangent of theta, we said, was y over x. That was one of our equations that we jumped back to. And the tangent of 5 pi over 3 is negative square root of 3. So this gives us the equation y equals negative square root of 3x. So let's fill in our general information. Our shape, if we just have a radius, is a circle centered at the pole. Circle centered at the pole. And the general form of this shape is r equals, let's go ahead and use the variable k, where k represents any number. And if we have just a graph that's based off theta, this is a line through the pole. So the line through the pole, and the general form of this is going to be theta equals k. Well, what happens if we have an equation like this? Do you guys remember from last time where we talked about, our sine of theta? Our sine of theta is equivalent to the variable y. So this graph should be the line y equals negative 3. And this is one of the benefits of having that rectangular coordinate system on there as well. We're able to draw that in fairly efficiently. If we go over here, if you notice, we have r equals 2 cosecant theta. R equals 2 cosecant theta, not quite what I'm comfortable with, just because this isn't r sine or r cosine. But if you remember, we could multiply both sides by sine theta. And by multiplying both sides by sine theta, we get r sine theta is 2. And remember, cosecant times sine is 1. So we just get the line y equals 2. So really, these two equations are synonymous with each other. They are both horizontal lines. So these are horizontal lines. And we have this as r sine theta equals k. Or we could also generate that horizontal line if we see r equals k cosecant of theta. Now, one of the explorations that I really want to go into is, if I'm working in a polar system where I'm working with angles, how is it possible that I'm generating a horizontal line? To answer that, I am going to go to GeoGebra. This GeoGebra link, I do have it linked in our notes. We could take a look. Shout out to Gabriela Sanchez. Hopefully I said her name correctly. I do like looking at this because this actually gives us a nice deeper connection to our polar and our rectangular at the same time. I am going to be working as we go further with just this one, created by one of my favorite GeoGebrists, Tim Brzezinski. Again, hopefully I'm saying his name right. But looking at the connection between a rectangular and polar just a little bit more. If you notice, I actually have this graph of, it's in terms of x. It's a limitation to GeoGebra, but we can work with that. So this is really the graph of r equals 2 cosecant theta. Now, as we start generating our angle, one of the things that we should notice is this radius that we're graphing right here actually connects to the length of the radius that I'm graphing in the polar form. So this is graphing in the rectangular system. This is graphing in the polar system. And remember, our goal is, can we do everything in polar? But how this polar gets created, it's very beneficial to make that connection between the rectangular and the polar. So as you're graphing, if you notice, this horizontal line actually gets created as we go the angle from 0 to pi. And one of the interesting things is, how is it that we're creating a horizontal line horizontal line going this way, or even at the angle of 0, how's it creating that horizontal line when theta equals 0 or theta equals pi? This is one of these neat aspects that if you're working in a polar system, this is where parallel lines could actually meet at infinity, something that they talked about during the class. But this is an application of where, okay, where's the end? How is it possible that a horizontal angle is going to give us a just a point way up here? That's because if we go out infinitely many units on the x-axis this way, it's going to generate just a point over here that represents this horizontal line. So we could go on to the rest of our information. It's a very cool exploration that parallel lines actually could meet at infinity. So next question is, as we go from 0 to pi, that's how this horizontal line was created. What happens when we go down into quadrant 3 and quadrant 4? With quadrant 3 and quadrant 4, shouldn't we have a line that's horizontal down here as well? Well, if you notice, and I'm going to jump up here, if you notice from the graph of cosecant, remember that from chapter 6, this graph of cosecant, the radius ends up being a negative value. So what happens is, even though the angle is pointing into quadrant 3, it has a negative radius, so it's generating that same horizontal line back in quadrants 1 and 2 because of the negative radius. So again, I like this app because it shows what we know from chapter 6. This is our graph of cosecant, I guess 2 cosecant, but what it does in the polar system is it creates a horizontal line. Now, how would we do that for example 3? Let me go back to my notes. For example 3, in order for us to get this and be able to graph it into GeoGebra, we would have to divide both sides by sine. So r sine of theta equals -3, divide both sides by sine of theta, and we get r equals -3 cosecant theta. So if you do want to use GeoGebra to kind of help you take a look at what these graphs look like, you always need to solve for r, which is why one of those skills that we learned last time was to solve for r. So let's continue on. Our cosine equals 4. So if our cosine equals 4, very similarly to what we did with the previous problem, that our cosine is equivalent to x. So this should be the line x equals 4. And that line is a vertical line. So our shape is vertical line, vertical line. The general form of this shape is r cosine theta equals whatever that k value is. This is going to be one of the last ones I'm going to graph into GeoGebra for the moment. Yeah, okay, I'm just kidding. I like to use GeoGebra a lot. But let's go ahead, look at this and say, all right, our cosine of theta equals 4. Quick jump back. How do we graph this into GeoGebra? We once again have to solve for r. So r is going to equal 4. If we divide by cosine, that would be 4 secant of theta. So in GeoGebra, r equals 4 secant theta. 4 secant. And remember in GeoGebra, at least for this one, we have to call it x. Now, you can see that we have the vertical line formed. Now, what's interesting about this is, as we start off at an angle of 0, this vertical line actually gets created going in the upward direction. And then this goes all the way up to infinity. And just like before, we now have a line or an angle that's pointing straight up here, but somehow it's creating a point over here. Once again, parallel lines are going to meet at infinity on different systems. And now, if you remember, cosine is negative, cosine and secant are negative in quadrant 2, which is why it's generating this angle down here. And so by the time we get to pi, suddenly that line actually met up with itself, and then we can continue on. Once again, we still have a negative radius here for quadrant 3. And then quadrant 4 starts here, and this is where we're generating a positive radius because once again, secant and cosine are positive in quadrants 1 and 4. And so we create this vertical line. So specifically, this vertical line gets created twice, once from 0 to pi, and then again from pi to 2 pi. As you look into some of the upper levels of calculus, mainly Calc 2 at college level, you start actually working more with the polar system. And then if you go into multivariable, you go from the polar system into what we call the well, we can go spherical system, but I was trying to think cylindrical system, but that would be 3 dimensions. So for right now, polar is kind of like the stepping stone as we get into further graphing. So if our graph is immediately in the secant form, hopefully you recognize this is equivalent to the r cosine theta is -3. So I am going to go ahead and graph that. So r cosine theta equals -3, which is that vertical line. So once again, this is a vertical line. Please remember vertical is spelled C-A-L, not C-L-E. And that general form would be r equals k times secant of theta. So quick recap, a circle centered at the pole is just r equals, a line through the pole is theta equals. A vertical line, we have horizontal line, we have 2 separate forms for it. You could either start off as r sine or r equals something cosecant. And then our horizontal lines are r cosine theta equals, or r equals something times secant. So what happens if you have r equals -4 sine theta? So just do a quick recap because these skills are so important to be able to match up the 2 systems. If you remember with a problem like this, we multiplied both sides by the variable r, and we have r squared is -4 r sine theta. So converting to rectangular, x squared plus y squared is -4y. And if you remember, what we did was we brought that y over to the other side so that we could see it in its rectangular form. We have to add 4 to both sides, and that adding 4 is to complete the square. I realize I'm jumping through a lot of skills here. There's an assumption you remember a lot of those skills that we've been working with all year. So this is actually a circle, and this circle is centered rectangularly at 0, -2. So the circle centered at 0, -2 with a radius of 2. I can go ahead and try to generate that. So 0, -2 is my center, and a radius of 2. This is where, once again, I like that I have that rectangular system on the polar system as well. And so we should have a graph that'll look like this. So one's not quite as easy to draw, but that's okay. So that's what we should have. Let's go ahead and take a look back at GeoGebra to see how this one's actually created. So I am going to say r equals -4 sine theta, or in this case, we have to type in x. And as we watch this graph get generated, from 0 to pi over 2, we're in quadrant 1. And if you remember, the sign of any of those angles in quadrant 1 are going to be positive. So our radius will be -4 times a positive value. So for our quadrant 1, we can see how this is generated. If you notice, our radius ends up being an actual negative value because it'll be -4 times a positive number from quadrant 1. So from 0 to pi over 2, we get half of the circle. From pi over 2 to pi, we get the other half of the circle. So what ends up happening is this graph gets created twice. From 0 to pi, we create it once, and then as we continue around, we create it that second time. So you'll find with a lot of graphs, there are going to be a lot of symmetry that we're going to be referring to. That's going to be in the 3rd video of today's series. But we're going to take a look at these symmetries and see if we can quickly take a look at what these graphs are going to look like based off of symmetry. That way it cuts our work in half and then makes it more efficient to look at these graphs. So once again, from 0 to pi, they have negative radii. And then if we go from pi to 2 pi, sine is negative in quadrants 3 and 4, but also multiplied by the negative mean that we're going to end up working with a positive radius. So this is actually a quadrant 1 with a negative radius, quadrant 2 with a negative radius, quadrant 3 with a positive radius, and then quadrant 4 with a positive radius, which is why this graph gets created twice. So this is a circle. And the circle is on not the polar axis, not the y-axis. This is on the theta equals pi over 2 axis. And the reason why it's theta equals pi over 2 and I'm going to highlight this. It's because of this sign. So sine gives us, if you remember sine, sine is an odd function. With that being an odd function, it has some symmetry working with, actually, probably a better way of explaining it is sine follows the y value. And since sine follows the y value, we're going to see a lot of things happen over the pi/2 axis. So this is r equals some number times sine of theta. So this is a circle. Now, what happens if our graph looks like this, where our secant theta equals 6? If we multiply both sides by cosine, we get 6 cosine of theta. And this would be a great time to take a guess and say, what do we think this graph is going to look like? Just occurred to me that you were watching one screen. Here's a graph that I created and worked on. So there's our shape. If we go into GeoGebra one final time, let's take a look at the graph of 6 cosine of theta. This time we are on the polar axis. So we are on the polar axis due to the fact that we have cosine of theta. If we have sine of theta, we're going to be on the, so if we have sine of theta, we're going to be on the theta equals pi/2 axis. If we have cosine of theta, we are going to be on the polar axis. And our furthest distance, and this is where we're going to start looking at this a little bit more analytically. If you remember, the range of cosine goes from -1 to 1. So the largest radius, is going to be 6 times 1, and that happens at theta equals 0. So at theta equals 0, we have a largest radius. Now, we will also have our smallest radius. So smallest radius is going to be 6 times -1, and that happens when theta is pi. And I'll go into a little bit more detail about how we're going to create these really with video number 2. So at theta equals pi, so if you remember, we're going to be looking in this direction. I'm going to erase that, but if we're looking in that direction, we end up going backwards to a negative radius of 6. So is that helpful creating the circle? Not really, which is why knowledge of what these graphs look like is very, very helpful. So the other general one I'm going to look at is what happens when our radius is 0. And our radius is going to be 0 when cosine is 0, when cosine of theta is 0. So that happens at theta equals pi/2. So we're looking upwards at pi/2, but that gives us a radius of 0. So how do we create this graph? I know what it looks like, and I know what it looks like based off of what we can see on GeoGebra here. Let me go ahead and walk into this for just a moment. So to take a look at this graph, I'm going to give you a sneak peek as to how we're going to graph everything else. We're going to look where sine and cosine are going to equal 1/2 to help us generate some nice points. But as I said, we want to know generally what the graph's going to look like, which is why I've been going through all these different ones saying what are the basic shape and what are the general forms of the shape. Having knowledge of what the equation gives us will help us generate these graphs more efficiently. So how we're going to do it, since we're working with cosine, so I'm going to work with this r equals 6 cosine of theta. Where does cosine equal, or what are the important theta values? So the theta values I'm going to look at are when theta equals 0, and that radius that we're going to get is 1. This is where I say, where does cosine equal 1/2? Cosine equals 1/2 at the angle pi/3. And so our radius is going to be 6. I said 1, that really should have been 6. Our radius is 6 times 1/2, or 3. So as I go out along the pi/3 angle, I end up working with a radius of 3. And then pi/2 gives me a radius of 6 times 0, which is why I have that point right there. If I go to pi/3, my radius is going to be 6 times -1/2, which is -3. So if I go along 2 pi/3, I end up graphing a negative radius. And this is where we can see this circle actually develop, just like I showed you in GeoGebra as I increase the angle, but we can see this circle created. Now, the one last point I'm going to throw on here, so these are the points that I really look for on quick graphing, is what happens when theta equals 5 pi over 6. I was going to say pi over 6, but let's continue on with 5 pi over 6. Our radius ends up being 6 times the square root of 3 over 2. Now, not a very happy number to have to come up with. So what I'm going to do is I'm going to throw this into the calculator. 6 times the square root of 3 over 2. So 6 times square root of 3 divided by 2. And yes, I do realize that we could have said 3 times the square root of 3. This gives me a radius of 5.19. And this should have been negative because we're working with 5 pi over 6. So if I follow along here and I go out to a radius of 5.19, that radius of 5.19 actually is about right here. And once again, we can see how that circle is being generated based off of the angles. Now, as we start focusing a little bit more on what does that 6 represent, the 6 actually represents the diameter of the circle. And we could check that with example number 7, that this -4, or more specifically, the 4 ends up being the diameter of the circle that we have here. The reason why where that negative comes into play is it's downwards as opposed to upward. In this one, our diameter of 6, the circle with the diameter of 6, is upward in terms of x, meaning this is our positive x values. So if I know that the diameter is 6, that means the radius is 3, and I can actually generate these points very, very efficiently as well. So does our circle have to be perfect? No, and thankfully not, as you can see my very sketchy drawing there at the end. So just to fill in the rest of our notes, our shape, this is going to be a circle on the polar axis. So with, let's go ahead and say radius of 3, or you could say diameter of 6. And the general form of the shape is if we end up with r secant theta is k, or r equals k cosine theta. More specifically, we should see it as the r equals k cosine theta. Now, this is where, if we're in the classroom, I would highlight this a little bit more. What's the difference between these two graphs? If you notice, the sine of theta has a domain of all real numbers. So our graph that we have here is accurate, but secant does not have the domain of all real numbers. Secant is never, what is this? I guess the best way of asking that is, what is the secant of pi over 2? So our secant of pi over 2 that I have right here, secant of pi over 2 is actually undefined. So I really cannot generate that point. So what happens is this is a hole at the pole. So hole at the pole. Now this domain kicks in when you see our secant theta equals k, or our cosecant theta is k. These give you the hole at the pole. I am not going to emphasize that this year, specifically because we are not in the classroom. I would rather you focus on what are the general shapes, but I couldn't let that go because you know me. So this should end video number 1. We're talking about some general basic graphs, and we're going to then, in video 2, get into the graphs of what we call cardioids and limasones, and even lemniscates as well. So stay tuned for more mathematics. Yay!